Okay, so it's time to start. So, a couple of things we're going to cover, or main things we're going to cover today is first, talk about universal gates, what that means, and why they're called universal gates. And then we're going to learn about two other forms of digital logic circuitry. We've talked about SOP sum of products and POS product of sums, but there's two other forms that we haven't talked about yet: NAND and NOR. And then there's an activity on both these things. And then once you know the NAND and NOR, you can do the second part of lab one. So like I mentioned last time, at the end of today's lecture, you'll have enough information where you can do the whole lab one. Okay. After Tuesday's lecture, you could have done basically 2/3 of it, two of the three outputs, but you'll be able to do the third output after the lecture today. Okay. So, like I try to do every class, this is the agenda. And we're going to start with universal gates. And the universal gates are the NAND and the NOR. And I'm going to do examples in class to show you why the NAND is a universal gate. And then the activity, one part of the activity, is actually two parts of the activity today. One part of the activity, I have you use the NOR gate universally to do some problems. So a universal gate, what that term means is that with that gate, you can construct the other gates. So, we've talked about a NOT gate, right? Inverter. Talked about an AND gate. We talked about an OR gate. Talked about an OR gate. Well, with the NAND gate, you can make all those other gates just using a NAND gate or NAND gates, either singular or plural. I can make a NOT, I can make an AND, I can make an OR, and I can make a NOR with just NAND. Okay. And you can also make all the gates with just a NOR or multiple NORs. And that's why they're called universal gates. So you can't make all gates with an AND, and you can't make all gates with an OR. Okay, only NAND and NOR are universal gates. Okay, so we're going to start with showing how a NAND can be used as a NOT, okay, or as an inverter. And to see why this is so, you got to look at the truth table of a NAND. Okay, so remember, I had this up on the board a couple of classes ago. An AND is equal to an AND with an inverted output, right? So when you look at the truth table of a NAND, it's the opposite output as what you have with an AND, right? Because with an AND, you only get a 1 out when all the inputs are 1, right? Otherwise, you get a 0. With a NAND, it's just the opposite of that, right? With a NAND, you only get a 0 out when all inputs are 1, and otherwise you get a 1 out. Okay. Well, one way, and there's actually two ways, and I'll show you both ways. One way to make a NAND into a NOT is you take your NAND and you connect both inputs together. You see what's going to happen to our truth table when we connect both inputs of the NAND together? Because if I connect two inputs together, what does that mean about those two input values? Could they ever be different? By physically connecting together, could one input be 0 and the other input be 1? No. When you physically connect inputs together, that forces those inputs to be the same value. Now, this is where having a circuits class is a little advantageous. And again, you're not going to be tested on circuits, and if you haven't had circuits, don't worry about it. I'll get you questions. But if you had a circuits class, when you connect two inputs together and you make them the same node, they have the same voltage. And remember, that's what zeros and ones are, right? The representation of voltage values. When I physically connect those together, they're either both going to be 0 or they're both going to be 1. So effectively, this truth table just becomes the first and the last row, because these two middle rows are not possible when the inputs are connected together. And look, when both inputs are 0, you get a 1 out. When both inputs are 1, you get a 0 out. And that's what a NOT gate is, right? A NOT gate will always be the opposite of what that input. Okay, so that's one way to make a NAND into a NOT. You just tie or connect. You got a question? Oh, okay, great. Thank you. All right, there's another way that you can make a NAND gate into a NOT gate. Okay, and this way you're not connecting the inputs together. And to understand this method of making a NAND into a NOT, it's advantageous to split the truth table in half. You're right there, right? Put that green line. And then just look at the bottom 2 rows. Okay? Just look at the bottom 2 rows of this truth table. Can you see that if I make one input to a NAND gate equal to a 1, the other input compared to the output is opposite, right? Because you see here these 2 rows where the A input is 1. If B is 0, the output is 1. If B is 1, the output is 0. So you see you have a NOT gate between that input that you don't connect to 1 and the output. So you see, if I did this, if I took a NAND gate and I connected one input to a 1, and say I call this other input A, well, the output would be not A. Right? But whatever I call it now, I could call it anything, right? I could call it C if I wanted. It doesn't matter what I call it. It's just I'm always going to get the opposite out. Right? The out of the NAND gate is always going to be opposite this input if I connect this to 1. Okay, so everybody see that? What if it's a 0, 0? Well, if I physically connect an input to 1, this could never be 0. Oh, yeah. Yeah. Now, we will talk about this upper part of the truth table when you do connect one input to a 0. See, because if you look at the upper part of this NAND gate truth table, if you connect one input to 0, yeah, well, actually, it doesn't matter. I mean, you don't have any inverse relationship between like B and the output. Okay? But we will get to something similar like later on, like looking at that truth table again. But right now, it's just the bottom half of the truth table that shows this. Okay. All right. So now let's move on. You can also use a NAND gate to represent an AND. Actually, it takes more than one NAND gate to represent an AND gate. And this goes back to something we talked about last week, and that's what's a NAND gate equivalent to? In fact, you know, NAND is short for not AND. So what is a NAND gate equivalent to that we talked about? Right, an AND with an inverted output, right? So a NAND is equal to that. Remember, it's equal to an AND gate with a inverter on the output. So if I take a NAND, right, which is equal to this, and then I invert the output of the NAND, well, now I'm back to an AND, right? Because if you have 2 inverters in a row, you're back to where you started, right? So you see, if I just did this, right? If I just took a NAND, which is equal to an AND with an inverter on the output, and then I put a NAND that I'm using as an inverter, well, now this together is an AND. Right, so you see 2 NAND gates in your AND. Okay. Any questions on that one?
Where's like the rectangular box directly to the left of the NAND?
Say that again. We're looking at this.
Yeah, like the rectangular.
Oh, this?
Yeah.
Oh, this is the 2. These are the 2 inputs being connected together.
So it's the same as just drawing 2 inputs.
Yeah, like this is A and B, and we're just connecting them together.
Okay.
Yeah, once you connect them together, like where I draw this line doesn't matter. I could draw this line here. Yeah, it doesn't matter. So, but yeah, I'm just taking this diagram that's a NAND as an inverter and just putting it at the output of this NAND. Okay. Is that okay?
In Nevada, how would we take one?
In Vivado, how would you, let's see. Well, we haven't gotten that far yet. So far in Vivado, all you've been doing is writing Boolean expressions. But starting next week, we're gonna get to like, if you have multiple circuitry, how you connect things together. We haven't really connected things together yet in Vivado, but we will get to that. Well,
So we don't need that for this time.
no, you're still writing expressions, you're still writing Boolean expressions, yeah. I mean, one place where you have been connecting things in Vivado is in your sim file. You know, when you write the design file name, and then you put UUT for unit under test, and then in parentheses you have like dot, input from your design source, and then parentheses and input from in your sim file. I mean, there you're making a connection. You're making a connection from the inputs in your design source to whatever you call the inputs in your sim file. And you're gonna see next week when we get to something called structural modeling, that you do the same type of syntax when you're connecting multiple circuitry up in a design source. So, I mean, your question is a very good one. It's just, we're not sort of there yet, but we're gonna get there. Yeah. Okay, any other?
Normally, for the AND gate, other NAND gate, why can't we just do the AND?
Okay. Yeah, that's a great question. I was gonna talk about it in a little while, but since you asked it, let me answer it now. Yeah, the question is, well, why even bother with this, right? Like, why not just use a single AND gate? Why make it more complicated? Well, to back up a little bit, remember we talked about with SOP and POS, right? Sum of products and product sums, right? The two different forms prior to today. That a reason to have, it's nice to have different forms is that, it gives you different options that, one form might give you less gates than another form. And now here, clearly, as you're pointing out, this would actually give us more gates, right? Than just use a single gate. But you see where it can be advantageous to do some sort of logic circuitry using just one gate. And this was more important back in the day. I mean, back when I was your age, up to maybe 20 years ago or so, this was more important than it is now. Now, it's not like it's not important at all, but it was much more important back in the day, because back in the day, instead of having these programmable ICs that we have now, like that FPGA that's on your basis board, which basically has every single gate and type of logic circuit inside. Well, back in the day, you had individual integrated circuits that only had one type of gate. You'd buy an IC, and inside that IC might be 4 AND gates. Then you have a whole nother IC, another separate IC that only had OR gates. And you had another IC that only had AND gates, and so on. But you didn't have the ICs with all the different logic circuitry that was programmable back then. So you see, if you could do everything in one gate, that meant your purchasing department, whatever you worked, was really happy, because they just could order one type of IC. And when you order things in bulk, you get a better price. So it's much more cost effective if you could just use one gate. Even though there might be more gates, since it was one gate, it could be more cost effective. Now, like I said, that's not as important anymore, but it's still somewhat important, because what I was talking about there with the individual ICs, that's like component level. What's on a printed circuit board, or on the breadboard if you're prototyping. But still, at the silicon level, like when they're making the actual circuitry inside the IC out of silicon, it's good to have everything just the same gate. Now, I know EEs, when you take your first circuits class, there is a manufacturing portion of that class where you learn a little bit about how ICs are made. Unfortunately, I think the CPEs with the new circuits electronics sequence that they have, the 115, 215, I don't know how much manufacturing is covered in that sequence because I wasn't involved with the development of it. But anyway, when you take a class that talks about how ICs are made, you'll have a better understanding, why it would be nice just to have one gate. It basically relates to just having to do one image in silicon, which again can be cost effective. So, I mean, the quick answer to your question is sometimes using the same type of gate is more cost effective. That would be the short answer. Okay, but great questions. All right, you ready for the OR as a NAND? Using a NAND as an OR gate. Okay, this is where De Morgan's comes up. De Morgan's tells us that a NAND is equal to what? An OR. It's not just an OR, what else? OR with inverted input. So you see a NAND is equal to an OR with inverted inputs. That's what a NAND is equal to. Right, so a NAND is equal to this, an OR with inverted inputs. Well, if I take a NAND and now I invert the inputs, right? So I put NANDs as inverters. Do something like that. Well, now that's an OR, right? Because these inverters here basically cancel these out and you're just left with an OR. Does that make sense? Is that a question?
Oh, those are all NANDs right there. That's not like on the box there.
Well, these are NANDs that are connected up to act like an inverter. Because remember, if you take a NAND and you connect the two inputs together, it acts like an inverter. So you see, that's what we're doing here is we're putting inverters, well, NANDs as inverters at the input of a NAND that's equal to this. Because these NANDs as inverters are going to cancel these inverters out. And this right here, this would just be an OR.
What's the NAND act as a norm? Oh, what I mean, or
Well, this goes to De Morgan's theorem. This is part of De Morgan's theorem that a NAND is equal to an OR with inverted output. I mean, we could prove it by doing a truth table of a NAND and doing a truth table of this, and you would see the outputs are the same. But yeah, this isn't new. We talked about this, right? We went over De Morgan's. Remember, this is one part of De Morgan's, that a NAND is equal to an OR with inverted inputs. And then what's the other part of De Morgan's? There's two parts to it.
Is the OR is equal to 20%?
Right, exactly. Yeah, that's the other part of it. Remember when we had to go from, we did the derivation last week from SOP to POS. Remember we used De Morgan's twice, and we were using each one of those one time within that derivation. Okay, so now lastly, and this is sort of extra, if you will, because once you show that you can use a NAND as not and a NAND as an OR, well, of course you could use it as a NOR, right? Because what is a NOR equal to? A not OR, right? So it's an OR gate with an inverter. An OR gate with an inverter on the output. So if I just take this circuit, right, which is using NANDs as an OR, and then connect this NAND as an inverter to the output of this, right? So I have 4 NAND gates, that would be a NOR. Right? So if I just took this, right? Because this is an OR. And now if I put another inverter on the output of that, this is a NOR. So you can see it would take 4 NAND gates to make a NOR. Okay, so any questions up to this point? Because one part of the activity today is I want you to do the same thing I did here, using the NAND as these 4 gates. I want you to do it using NORs. And it's the same approach. You would take the truth table of the NOR, and looking at that truth table, you should come up with 2 different ways to make a NOT. And then a NOR is a NOT OR. Right, so that will help you get this. Then, as mentioned earlier from De Morgan's, a NOR is equal to an AND with inverted inputs. And then once you have the AND, well, then you just invert the output. Using all NORs together. Okay, so it's if you understood this, you should be able to do the NOR. Okay. All right, so everybody okay up to this point? Because we're going to move on to something different now. Okay, we're going to move on to getting NAND and NOR logic representations, both equations and diagrams. So remember our chips, eggs, and salsa example? And remember we had, well, I should ask you, what form is this? SOP, this is SOP. Right, summer products. What form is this? Product is right. So this, we've talked about before, right? And, I showed you the derivation a couple classes ago, I think a week ago, of how you can go from SOP to POS. And, we've been doing SOP to POS, where you invert everything into the ORs, okay? Well, now this is something different. Now I'm going to show you how you can go from SOP to NAND. Okay, this is another form of equation. Now, before we do that, do you remember also with the SOP, what the logic circuitry would look like, the logic diagram? Like each one of these terms is going to give us what kind of gate? An AND gate, right? So we'd have 4 AND gates, and then what's the other gate we would have? OR gate, right? Because all the outputs of these ANDs would go into one OR gate, right? So in SOP, you have multiple ANDs, and you have a single OR, right? How about for POS? It's just the opposite, right? These get all ORed, so you're going to have multiple ORs, and then all those get ANDed together. So SOP and POS require 2 different types of gates, right? They require ANDs and ORs. These require more ANDs than the OR, and this requires more ORs than the AND. Well, why do you suppose we call this form NAND? Yeah, you're going to see it just has NAND gates. And we call that other form NOR because it only has NOR gates. Okay. All right, but let's see how we would do this, okay? So the first thing to go from SOP to NAND is you double knot each side of the equal sign. Double knot. Okay, because if I double knot both sides of an equal sign, I don't change anything, right? Okay, well, as we saw before, if you double knot just a variable like that, right, it's the same as just writing the variable. Okay, the next thing we're going to do, okay, and the whole reason we're doing the step that we're going to do here is to get the NAND. See, I can manipulate base 2 equations just like you can manipulate base 10 equations, right? When you're doing base 10 algebra, sometimes you want things in a certain form for a certain reason, and you perform certain operations to get that form. Well, that's exactly what we're doing here. Okay. So what we're going to do to get NAND is we're only looking at this here. Okay, just imagine that this top bar isn't there. Okay, we're just looking at this. So look, if I'm just looking at this, I've got this term ORed with this term, ORed with this term, ORed with this term, then the whole thing knotted. Well, what kind of gate is that? If you're ORing and then inverting the whole thing, that's what? That's a NOR. So you see, this is a NOR gate. This is a representation of a NOR gate that has inputs not C, G, not S, not C, G, S, C, not G, not S, C, not G, S. See, it's a NOR gate that's got these four inputs. And from De Morgan's, probably the third time I've asked this today, from De Morgan's, we know that a NOR gate is equal to a what? And with inverted inputs, okay? So that's what we're gonna do next, is we're gonna perform De Morgan's just on this. We're gonna take this NOR gate equation and show it as an and with inverted inputs. So these are my inputs. I'll write it down here. I invert the input, and now I AND it with this inverted input, and then I AND it with this inverted input, and then I AND it with this inverted input. So you see, that's taking this bar here and everything underneath and showing it in another form that's you know, that equates to. But I still have this bar. So this bar is still there. This is an E. So look what I get after I perform De Morgan's on this. Is now I've got these inputs inverted, and with these inputs inverted, and with these inputs inverted, and with these inputs inverted, the whole thing knotted. So if you just look at each term here, right? These inputs are ANDed together and then inverted, right? Inputs ANDed together, inverted, inputs ANDed together, inverted, inputs ANDed together, inverted. Just looking at a term right there, what kind of gate is that? That's a NAND. And then these NANDs are ANDed together, the whole thing inverted. What's that? NAND. So you see, that's why it's called NAND. So a circuit diagram, if you were to make a circuit diagram of this equation, it would look like this. You have 4 NAND gates. Right? They have 3 inputs. You know, this would be this term here, not C, G, not S. This would be not C, G, S. This would be C, not G, not S. And if I make a mistake, correct me. This is C. Sometimes I forget a not. Okay, and then you have another NAND gate that all these outputs go on. The output of this would be, sorry, my G's aren't getting very good today. You know, the output of that NAND gate would be these inputs all ANDed together, then inverted. And, you know, same sort of thing here. And same thing here. Right, and then all these inputs would be ANDed together and the whole thing inverted. So, you know, this equation would be at the output of that NAND gate right there. Right, so does everybody see how this equation represents NAND gates that are all getting ANDed, right? And it corresponds to this circuit diagram. Okay, everybody good? Okay, well, if you understood that, the next derivation is very similar. Okay, the next derivation is going from POS, product of sums, to NOR. Okay, so we start off double knotting again, both sides of the equal sign. And again, two knots over the same variable, same thing as just the variable. Okay, now I'm just looking at this here, ignore the top bar, just look at this bar and what's beneath it. You got this term, ended with this term, ended with this term, ended with this term, and then the whole thing knotted. So what kind of gate is that? All these terms ended and then whole thing knotted. That's an AND, right? This is an AND with inputs C forward with G S, C forward with G not S, not C forward with not G S. So you see, this is a NAND with these four inputs. And by De Morgan's, we know that a NAND is equal to what? 4 with inverted inputs. Okay, so I invert my inputs and then I OR them with the other inputs. So I take this input, I convert it, and OR it with this input, OR it. This input, convert it, OR it with this input. Make sure I didn't make a mistake. So I took that input, inverted it, ordered with this input, inverted, and then again, you get that top bar. So you see, now we have this NOR, this NOR, this NOR, this NOR. They're all being ORed together and then inverted. So can you see this is a NOR? Okay. So a NOR, you're going to have all NOR gates. Now, I'm not going to write everything here unless you want me to, because it's just like we did before as far as what you put for the inputs. Right, see that term would be a NOR gate, that term would be a NOR gate, that term would be a NOR gate, that term would be a NOR gate. And then to get the whole thing, that's why we have this NOR gate, right? Because these inputs go in, or these outputs of these NOR gates go into this input, and you end up with this equation, the output of that NOR gate. Is that okay? So to go from SOP to NAND, and to go from POS to NOR, it's really not that much. It's just doing De Morgan's once, right? We had to do more when we went like SOP to POS, right? Because we had to do De Morgan's twice there. So it's not as much as, what we had to do for, converting SOP to POS. Also, if you look at what we started with, let me take these away. Right? Remember, we started with SOP. Well, now look, if you look at NAND and SOP, can you see it's easy to go the other direction? If to go the other direction, these are your terms, right? You just take away the knots, like you take away this big knot, you take away the little knots, and then you take the terms and you just form them together. Right? And like over here, it's the same sort of thing, right? Here are the terms of the POS. So, just take away the knot. Whoops, I forgot this knot over here. You didn't correct me, right? I was missing a knot over there. But yeah, to go the other direction, these are your terms of your POS, but then you just got to change these fours to AND, and you end up with that. So to go from SOP to NAND, or NAND to SOP, or POS to NOR, or NOR to POS, it's fairly easy. Okay, when you first learn something, it's never totally easy, right? But but compared to what we're gonna do next, it's fairly easy. Okay, we're doing great on time. All right, I think we can finish this by the top of the hour. Okay, what's a little bit more work, it's not really challenging, I would say, it's just more work. It's going NAND to POS and NOR to SOP. Okay, again, NAND to SOP is fairly easy, and NOR to POS is fairly easy, but when you want to go NAND to POS or NOR to SOP, that's more work. Okay, and I've got examples here to show you how to do it. And it basically comes down to a key map. Okay, you just got to kind of go through a key. Okay, so let's start, or let's see how to do this with this example here. So here's a NAND equation. So like I just mentioned earlier, to go from NAND back to SOP, well, these are your terms right here, the AC, the not CD, the not AB, not C. So we just take those terms and OR them together to get the SOP. Okay, so this will be SOP for F. So it's just going to be AC ORed with not CD ORed with not AB, not C. All right, so does everybody see how I went from this to here? All right, again, I'm just taking each term, right? You take away the knots, and then you just OR them together to get the SOP. All right, so now the next step would be to put this SOP equation for F into a K-map. Okay, so since it's an SOP for F, what am I going to write in my K-map? Am I going to write zeros or ones? Ones, right? Because it's F, it's not F. Okay? So this is where we're going the reverse direction of what we did last class. Last class, you would have a K-map, and from the K-map, you would get the equation, either SOP for F or SOP for not F, depending on whether you're circling ones or zeros, right? Here, we're taking an equation and putting it into the K-map. So we're going the opposite direction. Okay, so but it's the same idea. It's just going the reverse direction here. So let's take it term by term. What would I write in the K-map? Where would I put the ones? Oh, I probably do. Let's see. Yeah, right at the point I should. Thank you. Yeah, and I forgot to put that up there. So I really appreciate it. Thank you. That's something I always forget. So yeah, put it like that. That should be good. There we go. All right, there we go. Good. All right, so what would I write in my K-map for this term A to C? It's a two variable term in a 16 cell. If you have a two variable term in a 16 cell K-map, what number grouping is that? Right, that's 4 ones. So where are the 4 ones going to go? What'd you say? 15, 14, 11, 10. Right, because those 4 would be all in the A row and all in the C column, right? So does everybody agree with that? That the ones would be here for that term? Good question.
There'd be one that it's not.
Say that again.
There are ones that it's not.
Right. When you have an equation for F, right? SOP for F, yeah, that comes from ones. Yeah, if it was not F, and you're gonna see we're gonna get to, yeah, we're gonna get to that. We will have a not F SOP coming up, but yeah, this is F. All right, so we did that term. Okay, now let's do not CD. So what would I write in my K-map for not CD? Where would the ones go? 4, 5. Yeah, it'd be this column, right? 1, 5, 13, 9, right? Because that column's in the not C and not D column. Yeah. All right. Okay, how about not A, B, not C? Now, how many or what grouping, number of grouping is that going to be since it's 3 variable? Right, it's going to be 2. So where's that 2 grouping going to go? Just be 4 and 5. Right, 4 or 5. Right, so these 2 here, they're in the not A row. not C column and B row, right? D changes, so that's why G drops out. All right, so everybody see how we got this? Right, it's just what you learned last class going the other way, right? All right, so that means all the other cells are zero. Actually, let me use a different color for the zeros. All the other cells here will be zero. Right, so I didn't miss any. So, can you guess what we're gonna do next? Because remember what we're trying to do. We're trying to get POS. Right, we're gonna circle the zeros because that's gonna give us what? That's gonna give us the reduced SOP for not F. And once we have an equation SOP for not F, what can we do to get POS? The Morgan's twice, right? Yeah. Okay, that's exactly right. So we just have to now write our SOP for not, right? That's circling the zero. So let's start with here, right? We've got a group of 4 here. Oh, one quick comment on the activities that I turned back that were done last class. I didn't mark off for this, but it's just a heads up for like the midterm. Always show me your groupings. Okay, like some people just wrote they filled out the K-map correctly from the compact midterms, but then they just wrote the equation. But show what your group. If nothing else on a midterm, if you make a mistake and you show the groupings, you're more likely to get partial credit than if you don't. Okay, so just make sure to show the groupings when you do this. Okay, anyway, so what term are we going to get from that grouping?
Not AC.
Not AC, yep. All right, and then what would you group next?
A, not C, not D.
Well, what are you grouping first? What?
Where just the 2 bottom.
These 2? Yeah, you can make a group of 2 like that. Okay, so what term is that going to give us? CA. And then what?
Not C.
Not C. Not D. Everybody agree with that? Okay, and then we still got this 0 up here, so what are we gonna do there?
0 and 2.
Right, oh, well, 0 is, oh, you could either do 0, 2 or 0, 8. So here's an example of there's more than one correct solution, right? Because I could group the 0 with this 8, or I could group the 0 with the 2. Either way, so you want to do 0 and 2? Yeah, that's fine. When I did it, I did 0 and 8. That's why I hesitated for a minute, because I didn't see that when I did it. So, okay, but what term is that going to give us? Not A. Not B. And what else? Is it not D? Yep, not. All right, so everybody good? Everybody agree? All right, so then what would I do next? Because I want POS for F, so this is where we do the Morgan's question. Either one is correct. Yeah, like when I did it, I did 0 and 8. Yeah, but Tracy or Sean,
Yeah.
I'm sorry. Yeah, I always do that when someone has a name where the last name could be a first name. I always mix it up. I'm sorry. Yeah, always correct me. Okay. Yeah, but Sean, I almost said it again. Sean did 0 and 2, so that's why. But either way is correct. So if you did 0 and 8, you'd have a different 3 variable term, but it's still the same reduced. It would still be 3 terms where 1 is 2 variable and 2 or 3 variables. So it's also a correct answer. Okay. Okay, but then we're doing De Morgan's twice, so you're inverting everything, ands the ors the ands, right? So this is gonna be A ORed with not C. Again, if I make a mistake, correct me. Like that, right? So did I invert everything and ands the ors? And ors the ands. Yeah, I always, and I advise also that you do the same thing. Always double check, because it's so easy to forget to invert something, or you leave an or in there or something. All right, so basically, you know, the added work when you go nan to POS is just you have to go through a K-map, basically. Okay, all right, well, let's do this example. Let's go from nor to SOP. Okay, so the first thing, this is our nor. So like we said earlier, it's fairly easy to go nor to POS, because all I do is I keep these terms, I get rid of the knots, and I just change this or to an and, right? So the POS for F is just going to be A ORed with C, ANDed with not B ORed with. Okay. Okay, what would we do next? Because, you know, we want to go into this K-map, but can I easily go from POS to a K-map? No. So what do I want to do to this before I go to the K-map? SOP. Yeah, make it SOP. And when we make it SOP, again, everything gets inverted, ands the ors the ands. So this is going to become not F. And then we're going to have, let's see, it's going to be not A, ANDed with not C, or B, ANDed with not D. Again, double check. I inverted everything, right? I changed ors to ands and ands to ors, right? So everybody agree I didn't make a mistake? Yep, I think.
So this was starting out with an S and P equation. How are the terms not inverted when you go from S and P to POS?
Are you talking about this here?
Yeah.
This is nor.
Oh,
Yeah, see, this is the nor, because that's what we're doing here. We're going from nor to SOP. So we're starting with nor. Because see, this term is a nor, this term is a nor, then those two nors would be ORed and the whole thing inverted.
yeah.
Yeah. So just like this example we did here, right? That we started with POS.
So you, okay, so you want the POS from the north and.
Right, exactly, yep. Yep. Okay. Any other questions? Okay, so now we have to put this SOP for not F into the K-map. So what am I going to write in the K-map now, since it's not F? Right, now I'm gonna write zeros in the K-map, right? Okay, so where am I gonna put the zeros for this not A, not C term?
Top left corner.
Yeah, right here, right? Everybody agree? That would be not A, not C. Okay, how about the B, not D?
6, 14, 12.
Say that again?
6, 14, 12.
Right, because it's gonna be these four here, right? There's some overlap. So. Right, that's gonna be a B, not D term. Everybody good? All right, so now we gotta put ones everywhere else. Okay, so now when I circle the ones, I'm gonna get what type of equation? SOP for F, right? And that's what we want. Okay, so we just gotta circle the ones. All right, so how are we gonna circle the ones here to get our SOP for F?
No.
Okay, we can do the bottom row. The group of four. So what term is the bottom row gonna give us? A not B. Everybody agree? A not B? Okay, what else do we have here? I'll let the person in the back know. You wanted to,
Oh, yeah, the column.
right here, this column? Yeah. Okay, you can do that column. And what term is that column gonna give us? CD, yep. Oops. CD. All right, what do you want to do next? Let's see, what haven't we covered yet? We haven't covered this one and we haven't covered that.
Actually, I just had a question.
Okay.
Index number 6, why is that a 0?
Why is
6 is 0.
okay, this goes back to here. Well, do you see where this came from?
Yeah.
Okay, well, let's see, we didn't make a mistake, did we? This B not D. We said it was these four. So yeah, because these four are in the B rows and they're also in the D column, because remember, this is the D over here, not D.
Okay, so that's the round.
Okay. Yeah, exactly. Yeah, remember the edges touch. Remember with the 16 cell, right? These edges touch, also these edges touch. And so you can, cross edges, right? All right, but we still have these ones not accounted for.
13, 15, I don't know what.
Oh, right here.
Yeah.
Yeah. Everybody agree that's a good grouping? So let's see, these four, what's common to these four? These four right here. A what?
G.
AD, yep. Let's see, we got one left. If you want to do that one, Lauren?
So 3 and 2, and then that would be dot A, not B.
Okay, but remember now, these edges touch. So we could do 2, 3, but we could do it with what else? Yeah, 11 and 10. Yeah, because again, these edges, in fact, I don't think we've had an example, at least at the board, maybe in the activity last time. But I don't think we had an example that showed these edges touch. We've had examples that show these edges touch, but also these edges touch. So yeah, you could do this. 3 and 2 along with 10 and 11, like these four right here. So what's common to these four, this four grouping?
No.
Not BC, yep. Okay, and then, if you wanted to, once you have SOP like this, you could easily go to NAN if you wanted to. So that would be going NOR to NAN. And then if you wanted to here, once you got POS, you can easily go to NOR. So that would be NAN to NOR. Okay. All right. So see, this class, what was new in this class is, what a universal gate is, and NAN, NOR. But then the rest of this class, don't you agree the rest of this class was a review of things we had talked about earlier, right? Because we had talked about not and OR and more and all that kind of stuff. And we had talked about POS and SOP, and we talked about K-maps. So this class, kind of ties together a lot of what we talked about previously with a couple of things that are new. Okay, so I would say that, if lecture today made sense to you, you're in a good place to this point, that things are making sense. Okay. All right, just a few more things you can get to work today. The first thing is I just want to show you the activity that's on Canvas. We didn't talk briefly about, you know most of it already from part 1. like I said, there's two parts to the activity. Two separate documents on Canvas under Meeting4. So like I mentioned earlier, show me how you would make an OR gate, a NOT gate, and an AND gate. Also include a NAND. It's not on here, but there should be a fourth one, NAND. So just like I showed you how to make these out of NANDs, I want you to show me how you make them out of NORs. Okay? And then the other part of the activity has to do with managing the OR. Yeah, here's the second part of the activity where I give you a truth table. And then from this truth table, I want you to get the reduced NAND circuit, like this diagram. So what are you going to do first? Since I want reduced, anytime you see reduced, what should pop up into your head immediately? The K-map, right? So you're going to have to put this truth table into a K-map. And then since we want NAND, what do we want to get from that K-map? SOP, right? Because it's fairly easy to go from SOP to NAND. Okay? All right. And then the second one is to get a reduced NOR expression from a NAND expression. All right. And here's the NAND expression. Now, again, I couldn't do bars in Word, so I did little tick marks. So this X tick mark, Y, Z tick mark, that's not X, Y, not Z. Okay, but you want to take this NAND expression and go to NOR. So this second part of this activity requires more steps than the first one. Okay. And then the last thing here. Oh, and my answers for the activities are up here. And the lab assignment. Well, like I mentioned last class, if you were able to get a successful simulation for your POS and SOP for lab 1, the only thing extra based on today's class is that we want you to add a third equation, so a third output for NOR, the reduced NOR. Okay, so your black box diagram for lab 1 should look like this. You got 4 inputs and you got 3 outputs, right? You got an SOP output, POS output, and NOR output. So when you download this to the board to demo when it's working, and you go through all the possible combinations, and how many possible combinations do you have since there's 4 inputs? 16. So you're going to have to show all 16 inputs in your video demonstration. And you're going to have 3 outputs. So you got to have 3 LEDs on your board to show each output. And should those LEDs all be in sync as you go through the table? So should they all be off at the same time and all on at the same time, following the same truth table? Yes. Yeah, that's the big point for this step. Even though we have different expressions in different logic circuitry, it all represents the same truth table. Okay, did you have a question? Yes. Yeah, that's like the big thing. Yeah. So I mean, if you're going through the truth table and you're not seeing that, right? Like you're seeing 2 of the lights in sync, but 1 isn't. It probably means something's not correct with that light's equation. Like something logically is not. Now it could be a physical thing too. It could be that the board has an LED that's defective. I mean, but it's more likely something in your code as far as the logic expressions. Okay. All right. So just like before, work on the activities at your table. Once the activity's done, pass it in. For the lab portion, you can either stay here or go someplace else to do it. Okay. You got any questions before you start on your work? Questions?
Yeah, yeah, you're right. I did that. But I didn't see how I did it here. So yeah, I was just being too fast. But yeah. So you understood this one? You understood that one? Okay, this one here is just that. Remember. Over here, remember we said a and is the same as an or converted to. Right, so that's how we go from here. So that's what I did here. I just wrote. Yeah. An and is the same as or. So.
There's my green. Oh, let me just get my marker here real quick.
Yeah, I understand. It's all expecting that, but I'm not.
Yeah, it's. Well. This is not getting here. This. Because we want you to command. So what we're doing is that. See, it's not. You convert it to out. Just like on the board. So you do the mean. The mean is this, and then I'm saying the converter to get rid of that. Oh, you know what I. So, well, because I'm using those names here, I can. Because again, when you have this person, the whole idea is to make it. Man, there's just more. Yeah. You're just being able to or like, you're gonna get more. Not making that more. Add a meander. What? Forgot this. Correct. Yeah, you see, it's very simple.